Swayam Prabha. Digital India. Educated India.
Welcome back to the course Mechanics of Solids. So, in the last lecture we have solved one numerical problem regarding this stress strain relation. Now, in this lecture we will be taking another couple of problems. Okay. Now, this is the second problem, okay, in this chapter, and problem says a batch of 2024 T4 aluminum alloy yields in uniaxial tension at the stress y equal to 330 meganewton per meter square, and by this time I hope that you still recall that what is your yield I mean stress, right, that is the value of y. Okay. If this material is subjected to the following state of stress, will it yield according to the Mises criterion and the maximum shear stress criterion, and these are the things are given: sigma x, sigma y, sigma z, tau xy, tau yz and tau zx. So, these 6 stress components are given, and you need to find out that whether this material will yield under this combination of stress. Okay. So, different stress components are there under the action of this state of stress, the material will yield as per Mises criterion and as per maximum shear stress or the Tresca criterion. So, let us see. So, now as you know that your maximum shear stress criterion or the Tresca criterion or Mises criterion, both the criterion I mean have been developed based on the principal stress components, right. So, in this problem sigma x, that is stress components are given in x y z coordinate system. So, we are going to find out the stress components in principal coordinate system, that is 1 2 3 coordinate system. Okay. So, let us start the problem. So, first find out the principal stress using the Mohr cycle. So, we will be using the Mohr cycle to find out the principal stress, and the stress, if you look at that, it is given sigma x is equal to 138 meganewton per meter square, sigma y is given minus 69 meganewton per meter square, sigma z is 0, tau yz and tau zx both are 0. So, hence we can conclude that this problem is a plane stress problem, right. You have sigma x, sigma y and tau xy. So, the stress is in xy plane. Okay. So, therefore, we can draw the Mohr cycle for that. So, let us draw the Mohr cycle. This is your sigma tau space. Okay. So, your sigma x is given as 138 meganewton per meter square, and tau xy is also given as 138 meganewton per meter square. So, your say x point is coming here, say, and tau xy is positive. So, that will be coming below your sigma axis. So, this is your x point, and this is somewhere it will be here, it will be your y point. Okay. So, with this I can draw a Mohr cycle. So, this is the Mohr cycle. The center of the Mohr cycle is somewhere here, that is your C, and this distance is small c. Okay. And this point will indicate major principal stress, this point will indicate minor principal stress. Okay. So, our objective is to find out sigma 1 and sigma 2. So, for that you know what are the things you are supposed to do. First you find out C value, that is nothing but sigma x plus sigma y by 2, that is coming as 34.5 meganewton per meter square. Similarly, R can be calculated as 138 minus 34.5 square plus 138 square. So, that comes as 172.5 meganewton per meter square. So, you have got C and R. So, therefore, your sigma 1 will be C plus R, that will be equal to 207 meganewton per meter square, and sigma 2 will be C minus R, that will be coming as minus 138 meganewton per meter square. And of course, your sigma 3, that is nothing but your sigma z. By default, sigma z is your one of the major principal stress, that is 0. Okay. So, you have got all the principal stress components, sigma 1, sigma 2, sigma 3. So, now you can apply your, first we will apply our Mises criterion. Okay. So, in the problem it is said that y value is equal to, that y is equal to 330, sorry, 330 meganewton per meter square. Okay. Now, as per Mises yield criterion, half sigma 1 minus sigma 2 whole square plus sigma 2 minus sigma 3 whole square plus sigma 3 minus sigma 1 whole square, right. So, that is coming as 300.76, which is less than y. So, therefore, it will not yield. Okay. Now, as per maximum shear stress criterion, let us see what happens. So, you have sigma max minus sigma mean, that will give you the maximum shear stress, right. That is coming as 207 plus 138 . Okay, modulus of that, I mean, because we are only interested the positive sign. Okay. So, fine. So, that is coming as, so 207 is your maximum major principal stress, and sigma 2 is your minor principal stress, that is minus 138. So, that is giving me 345, which is greater than y. So, therefore, it will yield. Okay. So, in that way actually you can find out whether the material will experience yielding or not, okay, by following these two criteria under certain combination of stresses. Okay. So, we will take the next problem. The next problem says a steel bolt and nut and an aluminum sleeve is shown in the figures. I will draw the figure right now. The bolt has 16 threads per inch, and when the material is at 60° centigrade temperature, the nut is tightened 1/4 turn. The temperature is, I mean, see, the bolt has 16 threads per inch, that is okay, but when the material is at 60° centigrade, then the nut is tightened 1/4 turn. Okay. Then the temperature is raised from 60° centigrade to 100° centigrade. Now, determine the stresses in both bolt and sleeve given, that is E, that is Young's modulus of aluminum is given, Young's modulus of steel is given ES, the thermal expansion coefficient of aluminum is given alpha A, and alpha A, that is the thermal expansion coefficient of steel. Okay. So, now the problem is something like that, you have an assembly of nut, bolt and sleeve. Okay. In that assembly you have given some 1/4, okay, or 1/4 turn of the bow, I mean nut. Okay. Due to that turn, I mean 1/4 turn of the nut, the bolt as well as sleeve will be experiencing some mechanical strain at 60° centigrade. Okay. Now, that assembly will be experiencing some mechanical strain, and that mechanical strain we can calculate. Now, once this assembly is under equilibrium and then you are raising the temperature from 60° centigrade to 100° centigrade, at that time only you will be observing the thermal strain due to the thermal expansion. Okay. So, you will be getting the stress developed due to the mechanical strain and stress developed due to the thermal strain, and these two stress components must be added algebraically to get the stress developed, total stress developed in the components. Okay. So, this is the idea. So, let us do or let us see the problem how we can solve it. First we will draw the figure. Okay. Okay. So, total depth of the arrangement is 4". So, this is your aluminum sleeve, all round aluminum sleeve, okay, something like your cylinder. Inside that you have the steel nut and this is the bolt, steel bolt and this is the nut, okay. And this total outer dimension is 3/4 inch and the inner dimension is 1/2 inch. So, we are solving this problem in FPS unit, nevertheless that is not a problem. Okay. Well, so now the first thing is that considering strain, please try to understand this thing conceptually. It is very conceptual thing, what is actually happening here. Considering strain due to stress only, that means mechanical strain we are considering first, okay, due to the tightening of the nut and other things. Okay. So, the state is one dimensional stress state, that is very clear from the figure. This is unidirectional, okay. In x direction there is nothing left out. So, only y direction you will be getting the movement or deformation whatever. Okay. So, from turning the nut the strain in bolt will be how much? When you are turning the nut in the bolt will be under tension, right, because you are applying here, you are giving the turn. So, it is trying to push that thing, push the sleeve. So, therefore, the nut, I mean this bolt will be under tension, right. So, that strain basically is nothing but say epsilon y b. Epsilon y is the strain in the y direction and b stands for bolt, okay, is equal to the stress developed in bolt in y direction divided by E b, that is the Young's modulus for bolt, that is nothing but your steel, okay, E b is nothing but steel, right. Okay. Now, for sleeve, what is happening for sleeve? For sleeve, the change in length say delta L is equal to now delta L for rotation, okay, plus delta L for bolt. Now, what is the meaning? Now, try to understand the concept, try to understand the mechanism, what is happening. So, when you are giving 1/4 turn of the nut, nut, then basically it will try to compress the sleeve. Okay. So, due to that rotation of the nut, you are getting the compression in the sleeve, but that will create some force on the sleeve and that sleeve will try to expand again due to this, because your bolt is getting extended and we are not considering any gap in between, right. That means, we are not allowing any gap in the assembly or we are not allowing any kind of say discontinuity in the assembly. So, the amount of turn of the nut will try to compress the sleeve and at the same time this bolt will try to get extended as I told you due to this rotation of the nut, and that extension will try to extend the sleeve also, right. So, therefore, this delta L total, the change in length of the sleeve will be consisting of the contribution from the rotation of the nut as well as the extension of the bolt, okay. And this part as given in the problem, that will be coming negative because that is creating the compression on the sleeve. So, that is nothing but the turn, how much turn you are giving into the lead that. So, this generally comes from your screw jack or this kind of threaded material, okay. So, this is the rule, right, okay. This much of distance or this much of length or the change in length is happening, okay, but that should be minus because that will be compressive in nature, plus your sigma y b by E b into L. Sigma y b E b is nothing but your epsilon y b, that is the strain in the bolt. The same amount of strain will be happening in the sleeve as well, otherwise you will be getting the discontinuity or the gap, right, and this much of deformation or the change in length is happening due to the rotation of the nut, okay. So, this has been given as 1/4 turn and 16, it is given in the problem the bolt has 16 threads per inch. So, 1/16 that is the lead plus sigma y b E b L, okay. Therefore, epsilon y s, what is that? Strain in y direction in sleeve, okay. So, strain in sleeve is nothing but this delta L by L, this delta L, that is a change in length in sleeve divided by the whole length, that is coming as minus 1 by 4, 1 by 16, 1 by L plus sigma YB by EB. Okay? Okay. So, from this I can get sigma ys is equal to epsilon ys into Es, that I can write from the stress strain relation, which is nothing but from this equation I can write minus 1 by 4, 1 by 16, and L is nothing but 4 inch, that is given, plus sigma YB by EB into Es. This Es stands for E sleeve, please try to understand. E sleeve is for E aluminum, okay. E sleeve is made of aluminum. So, Es is not like I mean E of steel, okay. This is E of sleeve, that this S is stands for sleeve and this B stands for bolt, okay. Do not get confused with that, okay. So, now from this, as given in the problem, EB is nothing but for your bolt, that is given as 30 into 10 to the power 6 pound per inch square, okay, and Es is 10 into 10 to the power 6 pound per inch square. So, by putting these values in this equation, I can simply get sigma YB minus 3 sigma Ys is equal to 11.7 into 10 to the power 4. So, say equation 1. Okay. By simply putting these values here, I am getting one relation between sigma YB and sigma Ys, okay, that I am keeping equation 1. Now, from equilibrium, I can write sigma Ys As plus sigma YB AB equal to 0. Sigma Ys As means the force in slip, and sigma YB AB is nothing but the force in bolt, right. So, the vertical force, that is the force in y direction in slip as well as bolt, the summation of all the forces must be equal to 0, because there is no external force applied in this assembly, right. I am not giving or I am not applying any external force, so that must be 0. So, this can be written as sigma Ys. Now, this is the cross sectional area 3 by 4 whole square, that is the outer diameter minus inner diameter. So, that gives the cross sectional area of sleeve plus sigma YB into pi by 4 into half. So, that is nothing but the diameter of bolt. Okay. So, that gives me one equation 5 sigma Ys plus 4 sigma YB equal to 0, say equation 2. So, now solving equations 1 and 2, we get sigma Ys equal to minus 2.75 into 10 to the power 4 pound per square inch, and sigma YB equal to 11.7 sorry 3.45 into 10 to the power 4 pounds per. Now, from here you can see that due to the mechanical strain, okay, your sleeve is experiencing the compressive force, compressive stress, and the bolt is experiencing the tensile stress, fine. So, this is coming due to the mechanical strain. Now, you have to consider the thermal strain. So, that we will be considering strain due to temperature change. Okay. Now, for that epsilon y b t, so T stands for temperature. Okay. So, epsilon y b t is equal to sigma y b t by E b plus alpha b delta t. Okay. Now, if you put all the values, you know E b is nothing but the E value of steel, alpha b you know, that is thermal expansion of the steel, and delta t, that is a change in temperature, that is 100 minus 60, that is 40. So, if you put all the numerical values, you will be getting epsilon y b t equal to sigma y b t 30 into 10 to the power 6 plus 5.12 into 10 to the power minus 4. Similarly, epsilon y s t, in a similar fashion you will be getting, if you put all the things, you will be getting sigma y s t by 10 into 10 to the power 6 plus 9.64 into 10 to the power minus 4. Okay. Now, your geometric compatibility says that delta y b t is nothing but delta y s t. Okay. So, anyway, so I will stop here today. In the next class, we will be continuing the same problem. Okay. So, geometric compatibility says that delta y b t equal to delta y s t. That means, the deformation in the sleeve must be equal to deformation in the bolt. Okay. So, I will stop here today. In the next class, we will continue the same problem. Thank you very much.